Welcome back to the course of Applied Elasticity. In today's lecture, we are going to continue our discussion on the contact problems, which we had started in the last lecture. So, to have a quick recap, the contact mechanics problem basically involves the solution of the contact patch generated or the contact area and the contact pressure profile or contact pressure distribution generated within that contact patch. Based on the geometry of the bodies coming in contact, based on the nature of friction present between the two contacting surfaces and the type of loading. So, contact mechanics problem basically deals with the solution of the contact stresses, the contact pressure distribution and area of contact generated when two bodies which may be rigid or elastic, at least one should be elastic and they are coming in contact. So, the solution of the contact problem depends on the geometry of the bodies coming in contact, type of loading and nature of friction present between the two bodies. Now, two types of contact problems we can broadly classify. One is contact between one rigid body with one elastic body, another is contact between two elastic bodies. In the previous lecture, we had discussed about the contact of a flat rigid indenter with an elastic half space, which falls under the first category of class of contact problem. Now, in today's lecture, we are going to talk about the contact between two elastic bodies. Now, contact between two elastic bodies is mostly described by the famous contact theory proposed by Hertz. So, this is called Hertz contact theory. So, first we will discuss about the assumptions of the Hertz contact theory, and then using that theory we will try to predict the solution of the contact problem, the contact pressure distribution and contact patch area prediction for the two elastic bodies coming in contact. So, here let us consider these two bodies. One body is B1 named as B1, body 2 is named as B2. They are coming in contact as shown in this figure due to application of the normal load P. So, P is the normal load which is applied between these two bodies along the z direction, and O is the point of contact. So, there are two contacting surfaces of body 1 and body 2 who are coming in contact at a single point O due to application of this normal load. So, Z1, Z2 are the normal directions for body 1 and body 2 respectively, and XY plane is called tangent plane between these two contacting bodies which is passing through point O. So, XY plane is the tangent plane and Z1, Z2 are normal axis on the XY plane which are normal along body 1 and body 2 respectively. Now, coming to the assumptions of the Hertzian contact stress theory. The first one is both the bodies coming in contact are described as homogeneous, linear, elastic, isotropic solids involving only two material constants. The next assumption is there would be a well defined tangent plane at the point or line of contact. Now, whether there will be a point contact or line contact, that depends on the initial geometry of the body. Let us say there is one spherical body which is coming in contact with another spherical body or coming in contact with a flat surface. For such cases, if a sphere is coming in contact with another body, the point of contact would be there, contact will be there at a single point. However, instead of a sphere, if a cylinder is coming in contact with a flat surface, in that case a line contact would be generated. So, sphere coming in contact with another sphere or flat face would result a point contact, a cylinder coming in contact with a flat face will result a line contact. Now, at the point or line contact there should be a well defined tangent plane. For the present figure, for the present problem of contact between body 1 and body 2, tangent plane is the XY plane. Now, bodies must be compressed along the normal direction to the tangent plane. So, the applied loading P should be perpendicular to the tangent plane for both the bodies, that is preserved here. So, Z1, Z2 are the directions along which the P forces, compressive loads are acting, and Z1, Z2 are perpendicular to the tangent plane, which is XY plane for our problem. Next, the contact is assumed to be frictionless. No friction is considered at the point of contact or within the contact span. Now, each body is modeled as an elastic half space to predict their local deformation around the point of contact. So, the bottom body is considered to be one half space subjected to load P coming from the top body B2, and then we will get the deformation pattern or resulting stresses on the bottom body, bottom elastic half space at point O using an approach similar to Flement solution approach. On the other hand, top body B2 will also be modeled as another elastic half space which is subjected to the upward load P coming from body B1, and which would also be solved by using a similar approach. The local deformation and local stresses on body 2 at point O can be obtained. So, both the bodies are being modeled as individual elastic half space for predicting their local deformation, and also the contact patch generated is assumed to be flat patch, and the contact patch area or radius of the contact patch is assumed to be small as compared to the dimensions of the body or as compared to the radius of curvatures of the body at the point of contact. So, radius of curvatures of both the bodies at the point of contact is much larger as compared to the size of the contact patch, and that contact patch must be flat. So, these are the assumptions for the Hertzian contact stress theory with which we will try to solve this problem of contact between two elastic bodies. Now, we are considering one point M on body 1, which is at a distance Z1. So, normal coordinate of point M is Z1, and Z1 value must be small, which is too close to the point of contact. So, this state is just two bodies are in contact, P is not yet pressed. So, this is when two bodies are just coming in contact without any pressurization. Once we apply the load P, there will be a finite patch generated. Now, there is a single point contact. Once P is applied, then there will be a finite patch of contact generated. So, M is one point on body 1, which is initially outside the contact span, and once P is applied, point M will come inside the contact span. That would be our approach. So, we are choosing any point M on the body 1 surface closer to the point of contact, and the Z1 normal coordinate of that point is written as A1 x square plus A2 x y plus A3 y square. This is kind of the approximate way of writing the Z1 coordinate with the help of two in plane Cartesian variables x and y. We are considering it to be a second order polynomial of the in plane Cartesian variables x and y for point M on body B1. Similarly, we can choose another point N, which is on the same normal line. The line joining M and N must be orthogonal or perpendicular to the tangent plane xy. So, the coordinate normal coordinate of point N on the surface of body 2 is Z2, which is written as B1 x square plus B2 x y plus B3 y cube, where both these Z1 Z2 are small. Those two are the 2 points on body 1 and 2 which are much closer to the point of contact O. Now, we can sum these two up. Z1 plus Z2 will give us the total normal distance between these 2 points M and N, which would be A1 plus B1 times x square plus A2 plus B2 times xy plus A3 plus B3 times y square. Now, x and y, these are the two in plane directions. We can always choose xy axis along the principal direction, so that this mixed term xy term A2 B2 term is set to 0. So, A1 B1 A2 B2 A3 B3 are some constants which depends on the curvature of the bodies coming in contact around point O. So, by choosing this xy axis to be principal direction, it is possible to write this equation as z1 plus z2 equals to ax square plus by square, just two terms dependent with x square and y square, where a and b depends on the principal curvature of the surfaces coming in contact at point O. Now, this equation, if you carefully look, this is basically equation of an ellipse. So, hence all such points M and N with mutual normal distance z1 plus z2 will fall or will form an ellipse, and thus once P is applied, the bodies are pressed against each other and elliptical contact boundary would be generated. So, one M I have taken on body 1 and N on body 2. If you take series of such points, if we keep on taking such points, all those points on body 1 and body 2 will generate an ellipse. If you look from top, all such M points on each of the body and all such N points on another body will be forming an ellipse, whose equation is given like this. Now, once the bodies are pressed in the normal direction, M and N points will be going towards each other, mutual distance will be reducing, and thereby an elliptical contact boundary would be generated. Now, moving forward, considering W1 to be local displacement of point M, this is the condition, that local deformation once the load P is applied. The previous one was in the unloaded case, once just 2 point contacts are there. Now, once we are applying the load, there would be local deformation of point M and N, which we can obtain by using the elastic half space deformation theory. So, W1 is considered to be local deformation of point M on body B1 along the normal direction Z1. Similarly, W2 is the local deformation of point N on body B2 along the normal direction Z2. These are localized deformations which is coming due to the applied load P. However, there will be some far field approach between these two bodies. So, as we are pressing two bodies with each other, there would be certain amount of contact path generated, because from these configuration it will be going to a configuration like this, where this much amount of finite contact span is getting generated, and hence the center of these two bodies will come closer to each other by, let us say, an amount delta. So, delta is the normal approach distance for far field points of these two bodies, and W1 and W2 are the respective local deformations of point M and N on body 1 and 2 respectively. Hence, initial distance Z1 plus Z2 for body 1 and 2, which was there before the generation of contact patch, that should be equals to this far field approach distance delta minus the local deformation of body 1 and 2, summation of that is W1 plus W2. If we assume our tangent plane, this xy plane, to be datum, that is a non-moving one, that is remaining where it is, top body is coming down, bottom body is going up due to application of this normal loads P along Z1 and Z2 directions. So, for that we can write that the far field displacement delta minus the summation of local displacement W1 and W2 predicted by elastic half space deformation theory should be equals to Z1 plus Z2. This gives us the change in normal distance between these 2 points. If this is true, then these 2 points M and N are just coming within the contact boundary, within the contact patch due to local compression as this load P is applied. So, this equation is true only when M and N points are coming closer to each other and going inside this flat contact boundary. So, let us say this point is M, this point is M. Now, they are overlapping points, they are coming and setting on each other. So, from this we can write W1 plus W2 is equals to delta minus within bracket AX square plus BY square. Now, for an elastic half space subjected to a normal pressure intensity, let us say Q, over a small patch, for that the normal displacement component using the Boussinesq theory can be obtained like this: 1 minus nu square by pi e area integral of q dA by r. This is simply extension of Flement problem. For the Flement case, a single point load, line load of intensity W was applied. Instead of that, instead of applying the normal load at a point, if we apply the normal pressure distribution of intensity Q over a small patch, over an area or patch of contact, for such case the Boussinesq theory predicts the deformation in a similar fashion as the Flement theory in the normal direction. Normal deformation as this: 1 minus nu square by pi e area integral q dA by r. Now, we can write both this W1 and W2 using these deformation predicted by the Boussinesq theory. Now, taking E1, E2 and nu1, nu2 to be properties of the body 1 and body 2 respectively, these equation can be written in this fashion. And then 1 minus nu1 square by pi E1 and 1 minus nu2 square by pi E2, these two terms can be taken as two new constants k1 plus and k2 respectively, and hence the equation becomes k1 plus k2 area integral of q dA by r equals to delta minus a x square plus b y square, where q is the contact pressure profile per intensity generated within the contact patch. So, now M and N are the 2 points which came into contact, come in within the contact patch. So, they are coinciding point, and Q is the distribution of the pressure profile within the contact patch, which can be related with the delta, the approach distance, using this equation. And K1, K2 are two integer numbers which we can obtain by using the material properties of two bodies. If two bodies are identical, K1 and K2 would be same. Now, moving forward, the pressure intensity variation Q can be obtained to be having a semi ellipsoidal variation, because already we had discussed the contact patch profile boundary is described by an equation of an ellipse. So, hence the pressure distribution within that contact patch would be semi ellipsoidal in nature. So, this is the contact boundary, let us say of semi major axis A, small a, semi minor axis small b, and the contact pressure distribution would be something like this, which is having semi ellipsoidal variation, which is q x comma y in 2D, and this q naught is the value of q at the tip, at the center, which is the maximum pressure intensity at the center of the contact surface. Now, using this semi ellipsoidal variation, we can write the total contact force. The total contact force applied is P, which is compressive in nature, and that is resulting this pressure distribution within the contact patch of the body. Hence, from the free body diagram, if you consider one body, load P is applied downward, and here this kind of contact pressure distribution Q is generated. So, Q integrated over this contact area should balance the net compressive load P applied on the body. So, P equals to area integral Q dA, and for ellipsoidal variation of Q, this integral can be obtained as 2 by 3 Q naught pi A B, and this maximum pressure Q naught for this particular case can be then written in terms of P as 3 P by 2 pi A B. Now, we know that the area of the ellipse is equals to pi a b. So, this 3 by 2 times P by pi a b can be written as 1.5 times P by the area of the ellipse. So, this P by area of the ellipse we can write as average contact pressure. If pressure is uniformly distributed over the elliptical area, then that would be called as Q average pressure. So, 1.5 times of the average contact pressure is generated at the center of the contact surface, which we call Q naught, or the maximum pressure generated at the center of the elliptical contact patch once two elastic bodies are pressed. Now, based on this theory, we are going to check the exact equation for the contact patch, the mutual approach distance delta and contact pressure intensity between the contact of two elastic spheres. So, last one was a general one. It is valid for spherical or any other non-spherical, a general profile. Now, we are specifically focusing for the contact between two spherical bodies. So, two elastic spheres are considered with radius r1 and r2, which are pressed against each other in the normal direction by applying this compressive load P, where this point O is the point of contact. Now, let us look into the point of contact, that region in a zoomed one, where small a, the area contact patch area is generated, which is having radius small a, and QR is the pressure profile distribution, which is varying radially over this contact patch. Now, considering this equation Z1 and Z2, which are distance of 2 points M and N in the normal direction for these two bodies lying on two bodies B1 and B2 respectively, considering the bodies to be sphere, we can get these values of A2 and B2 to be 0. These mixed terms are 0 because we are having the equal radius of curvature. Both the radius of curvature at any point for the sphere are same and equal. Thus, all the directions are principal curvature directions. So, A1, A3 for radius 1 for sphere 1 would be 1 by 2 R1, and for second sphere B1 and B3 they would be equals to 1 by 2 R2. Hence, using these equations of Z1, Z2 for the sphere, we can write for the first sphere Z1 is equals to R square by 2 capital R1 and Z2 equals to R square by 2 capital R2. So, these are the distances of those 2 points M and N, which are just normally above each other, and once P is applied they will be coming in contact and coming within the contact patch. So, hence Z1 plus Z2 we can write as some constant beta times R square, where beta is given as capital R1 plus capital R2 divided by 2 times capital R1 capital R2. Now, substituting it back in the equation of the mutual approach distance delta, which was delta minus W1 plus W2 equals to Z1 plus Z2. This is the equation we had derived for the Hertzian contact stress theory, where W1 and W2 are the local deformation of two bodies around the point of contact. Delta is the mutual approach distance for the far field points between two bodies, that is equals to Z1 plus Z2. And for the present problem of contact between two spherical bodies, we had obtained that Z1 plus Z2 is equals to beta R square. So, hence delta minus W1 plus W2 would be equals to beta R square, and we can write W1 and W2 in terms of this integral using the Boussinesq theory, which is K1 plus K2 times integral Q dA by R integrated over the total area equals to delta minus beta R square. So, this is the governing equation for the present problem, from which we need to find out the pressure distribution Q and delta. So, from this equation, if we are writing the pressure distribution, now if we recall the general case, the contact patch boundary was defined by an ellipse. Now, as the two bodies coming in contact are sphere, for such cases the contact patch boundary will be converted into a circular boundary from an elliptical boundary, and hence the semi ellipsoidal pressure variation will now be changed to hemispherical pressure variation within that circular boundary. So, we can write the expression of Q, the pressure distribution Q, as a function of radial coordinate r using this equation, where QR is equals to Q naught times square root of 1 minus R square by A square. This is valid within the contact patch, that is for R varying between 0 to contact patch radius A. Now, substituting this hemispherical pressure variation as proposed by this Hertzian contact stress theory here in this equation, and then evaluating this integral, we will be getting this particular equation where k1 plus k2 times q naught pi square by 4a times 2a square minus r square is equals to delta minus beta r square, where k1 and k2 are two constants, depends on the material parameter E1, E2 and nu1, nu2, Poisson's ratios and Young's modulus of both the elastic bodies coming in contact. Now, this particular equation to be true for all values of r within the contact patch, if I compare both the sides, you can see one term is constant. On right side, delta is a constant term, beta r square is r dependent term. Similarly, on left hand side also, the first term 2a square times the external constant, that is a constant term, then this external term times r square, that is r dependent term. So, this equation to be valid for all values of r, both the constant term and the coefficient of r square must be same for all the cases, and hence this can be true for all r only if we have the constant term for both the sides, r independent term on both the sides to be same, which would give delta equals to k1 plus k2 q naught pi square a by 2, and the coefficient of r square to be same on both the sides, which would give beta equals to k1 plus k2 q naught pi square by 4a. So, using this equation we can relate delta with q naught and a, we can relate beta with q naught and a. So, moving forward, if I remove delta from this equation and relate a with beta, then a would be coming out as k1 plus k2 times pi square q naught by 4 beta. Note that beta was an constant, geometric constant dependent on the radius of both the spheres r1 and r2. k1 and k2 are related with the material constant. So, all these are known quantities. So, from this equation we can relate the radius of the contact patch A with the maximum pressure intensity q naught generated at the center of this circular contact boundary, and total contact force P can be related with the pressure distribution, contact pressure distribution QR like this. P is equals to area integral of the contact pressure. So, from this is coming from the force balance of any one body in the normal direction. So, P is equals to area integral QR dA, for QR is having a hemispherical pressure variation like this. If you substitute this equation here, you would be getting P to be 2 by 3 pi a square times q naught. So, this gives us the total contact force, using which the q naught and P can be related as q naught equals to the maximum pressure intensity generated is equals to 3 times applied normal load P divided by 2 pi a square, where a is the contact patch radius. So, note that contact patch radius is unknown, that should be our output, and P is the known. We are applying the load, that is known. We know the geometry R1 R2 for both the sphere, means beta is known, and K1 K2 the elastic properties are also known for both the spheres. So, these are the known quantities. Our objective is to find out pressure distribution QR, that is q naught is unknown. We also want to find out A. Now, using these two equations, the first equation relates A with q naught, second equation relates q naught with P. So, we can either remove A from this equation or remove q naught from this equation, and using that we can relate A, the contact patch generated with the applied load P. We can also relate q naught with P, which would be independent of A. So, if we do so, the radius of the contact patch A in terms of applied load P, the geometry means radius of two spheres R1 R2 and material properties which are defined by these two constants K1 and K2 can be written like this. A would be cube root of 3 pi P times K1 plus K2 R1 R2 divided by 4 times R1 plus R2. This would be the radius of contact patch generated once the two spheres, elastic spheres, are coming in contact due to the compressive load P applied along the normal direction. This is the contact patch predicted by the Hertzian contact stress theory. Now, coming to delta. So, we can obtain the value of delta by using the equation delta minus beta r square is W1 plus W2. So, substituting the expression of A and Q naught there, the mutual approach distance delta can be obtained like this. So, the radius of the two spheres coming in contact would approach each other. The center of the two spheres, the far field points, any far field point of two spheres would be coming towards each other by this much mutual approach distance delta. And finally, the pressure profile distribution within the contact span QR, that is hemispherical pressure distribution, which is Q naught times square root of 1 minus r square by a square. Now, we had related Q naught with the applied total force P, which is P equals to integral area integral Q times dA. So, from that Q naught can be written the maximum intensity of the contact pressure at the center of the contact patch can be written as this 3 P by pi a square, and hence QR, the contact pressure distribution, is written as 3 P by 2 pi a square root over of 1 minus r square by a square, and this is valid only between the contact span defined by for the range of r from 0 to a. So, this gives us the complete solution of this contact problem between two elastic spheres of radius r1 r2, where we got the contact patch radius, which gives us the area of the contact patch, then the mutual approach distance of far field points of the two spheres, and the pressure distribution generated within the contact patch, which is QR. So, in this lecture we had discussed about the formulation of the Hertzian contact theory, and using that we had obtained the solution of the contact problems of two elastic spheres pressed against each other due to application of the compressive normal loading. Thank you.